Have you ever looked at a whole bunch of messy, scattered data and wondered how on earth we could use it to predict the future? Well, that's exactly what regression analysis is all about. It's kind of like a mathematical art form for finding a clear, predictable pattern that's hiding inside all the chaos of the real world. So let's dive in and see how it's done. So here's the fundamental challenge, right? Whether you're tracking something like stock prices or population growth or even radioactive decay, the data you collect is almost never going to be a perfect, clean line. It's noisy, it's chaotic. So the big question is, how do you find that hidden signal in all that noise? All right, so where do we even start? Well, first, we've got to face that chaos head on. We need a way to just look at all our individual measurements at once, just to see if our own eyes can pick out any kind of pattern hiding in there. And the very first tool we use for this is this scatter plot. Simple, right? Each one of those dots you see represents a single piece of data we collected. And you'll notice right away, it is not a perfect, clean line. It's a mess. But this beautiful mess, this is our starting point. But even in all this chaos, our brains are pretty good at finding patterns. We might look at that scatter plot and spot something that kind of looks like a straight line, or maybe a gentle curve, or maybe even that really dramatic swoop of an exponential trend. The scatter plot gives us our very first clue about the relationship that's hiding in the data. Now, making an educated guess just by looking at it, that's a great start. But for this to be science, we need to be precise. We need a real mathematical tool that can cut through all that noise and formally define that hidden trend we think we're seeing. And that tool is the line of best fit. I want you to think of it like a data detective, drawing the single most probable path right through the middle of all those scattered points. It's not a guess, okay? It's a mathematically calculated line that gets as close as it possibly can to every single data point, all at the same time. Okay, this is where it gets really, really powerful. This line, it isn't just a drawing on a graph. It's a mathematical equation. It's a recipe. So for a trend like radioactive decay, which we know is exponential, the equation often looks something like y equals a times b to the x. The whole game here is to find the perfect numbers for a and b that create the one single line that best fits our data. All right, so we've got our data and we've drawn a line through it. But how good is that line? I mean, is it a really solid fit or did we just get lucky? We absolutely need a way to measure, with confidence, how much we can actually trust this model we just built. And for that, we use a score called R-squared. Honestly, the easiest way to think about it is like a report card for our model. It's just a single number, from 0 to 1. A 1 is like a perfect A+. It means our line explains the data perfectly. A 0 is a total fail. It's a really simple, powerful grade that tells us how well our model actually fits the real world. And you can really see the difference here. On the left, with a high R-squared value, all those little data points are clustered super tightly around our line. That's what a strong, trustworthy fit looks like. But over on the right, you see how the points are scattered all over the place? That low R-squared value is basically a huge red flag, telling us, hey, this model is not a good predictor. The dream, of course, the absolute gold standard, is to get an R-squared value of exactly 1. That would mean every single data point we collected falls perfectly, exactly on our line. Now, let's be real. In the messy real world, that pretty much never happens. But it's that perfect score we're always aiming for. So here's a good rule of thumb. If your R-squared value is 0.9 or higher, you've got yourself a really strong, really reliable model. It basically means your line explains at least 90% of what's going on with the data. And once we have that kind of confidence, well, then we can move on to the most exciting part of this whole thing. This is it. This is where all that hard work really pays off. We've taken messy data, we've found its hidden trend, and we've proven our model is strong. So now we get to do something pretty amazing with it. We get to see into the future. So why did we go through all that trouble? Finding lines, calculating scores, what was it all for? Well, the payoff is right here. It's the incredible ability to make educated, data-driven predictions about what's probably going to happen next. The technical term for this is extrapolation. And yeah, it's as cool as it sounds. We are literally taking our trusted line of best fit, our proven model, and we're just extending it. We're pushing it out beyond the data we actually have, into the unknown. Let's make this super real with a pretty high-stakes example. Imagine we have data on radioactive decay from, say, the last 50 years. How could we possibly use that to know what the radiation levels might be in the year 4000? Well, extrapolation gives us a way to find out. So how would we actually do it? The process is surprisingly straightforward. First, we'd plot our 50 years of radiation data on a scatter plot. Second, we'd calculate that exponential line of best fit and, crucially, check that it has a very high R-squared value. If it's solid, then all we have to do is extend that line way, way out to the year 4000 on our graph and just see where it lands. That's our prediction. Look, this isn't a crystal ball, and it's not science fiction. It's simply applying a mathematically proven trend from the past and projecting it forward, making an educated guess that the trend is going to continue. It is a profoundly powerful way to turn information from the past into insight about the future. And that's pretty much regression analysis in a nutshell. It's a tool for finding the signal in the noise, and then using that signal to get a peek at what's coming next. So I'll just leave you with this thought. If you had the right data, what future would you want to predict?